Welcome. So today we are going to start the concept of electricity, and in the very first unit of electricity we need to know certain very important things. And the first important thing we need to know is the mechanism of flow of charge in metals. And to understand this mechanism, our physicist has developed a model, and the name of the model is the free electron model of electric conduction. That means the responsible candidate for carrying the electricity in metals are none other than by the free electrons. Okay, so in solid we have free electrons, but in fluid and gas we have both, like the negative ions and the positive ions, both can conduct electricity. Okay, now what are the how we are going to proceed into this free conduction of free electrons model of electric conduction. So we know that metal has free electrons. Free electrons are those electrons whose potential energy is zero. They have kinetic energy because of which they randomly move, but as such the potential energy with respect to the nucleus is zero. So when we talk about free electrons, they move randomly. So if an electron is here, they move randomly, they collide with another ions, and then they go in this direction, and then they again collide. So they have a random movement, and as a result, if I consider many electrons are there, somebody is moving in this direction, somebody is moving in that direction, some electron is moving in this direction, some electron is moving in this direction. So overall, if you take the sample and if you see the average velocity of all the electrons, average velocity will always end up to zero. That means there is no net displacement. The whole thing is so randomly organized that there is no net movement of the electrons. Electron going in that direction will not keep on going in that direction, but somehow will come back sometime in future, definitely, because it has to undergo many number of collisions. Okay, so we have this first important thing that if I consider u1 plus u2, this is small u, all these are small u, initial velocity. So if I consider that this is velocity u1, u2, u3, and there are n number of molecules, so u1 plus u2 plus u3 plus dot 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 till un divided by n, this is always equal to 0 for a given metal, where n is the total number of electrons. Now what happens when you apply an electric field to it? How do you apply electric field? You connect this with a potential difference. Let us say this is plus, this is minus. So when you connect this to a potential difference, it develops an electric field from plus to minus. So now what happens to the electron? Yes, they are moving randomly here and there, getting collided, but they started, so suppose from here it has reached here, so slowly they start getting drifted in this direction. Just imagine, this is a very layman style to make you understand. Just imagine that this electron undergoes 4 collision and comes back here again after 4th collision. That means net displacement is 0, correct? But here in this case, this electron goes first collision, second collision, third collision, fourth. In the 4th collision, by the time it gets 4th collision, from here, it has slightly moved here for having the 4th collision. That means you can say that because of the electric field, the electron has slightly drifted along this direction. And it is because of this drift, we say that the electron moves towards the high potential. But remember, direction of current is always from plus to minus, and you know from childhood days that direction of current is in the direction opposite to the movement of electron. So basically electron drifts in this direction whereas the current flows in this direction. So who helps the electron to drift? The electron gets started drifting because now they have some net displacement. It is because of the electric field which you provide. It is because of that it starts drifting towards the high potential. Okay. Now, based on this, let us do some derivations over here. So, this is a brief idea on how this potential difference helps the electron or helps the electricity to flow. So, it is this brief idea that electron starts drifting towards the high potential, and that is nothing but the mechanism of current. So, the first thing which we need to know is this relation between electric current current I and Vd. What is Vd? Vd here we defined as drift One is called relaxation time and one is called the mean free path. Relaxation time is that time. Relaxation time is basically the time between two collision. So if an electron hits first ion here, okay, now start the time. So it is going to hit another ion over here. So the time spent between two successive collision is called relaxation time. And the distance traveled during that time is called mean free path. Okay. So we will come to that, is there in the note, you can note it down. So the drift velocity is because of the electric field due to which it starts drifting along this direction. Now we have to establish a relationship between current and drift velocity. How this drift velocity decides the current. Now we know that current I is equal to Q by T, rate of flow of charge. And Q you can write as N times of E, where N is the total number of electrons divided by time T. What is N? Total number of electrons. Now before we proceed, I am going to define one more N, and this I am calling as small n. What is small n? Small n is called electron density, or number of electron per unit volume. Number of electrons per unit volume. Okay. Now why we have to define this? Now imagine this condition over here. Say that this is a conductor, a part of a conductor. This I have maintained at high potential and this I have maintained at minus potential, so that I am developing an electric field from plus to minus. This is my electric field E. So the current has to flow from high potential to low potential, but the electron, where it will get drifted, it will get drifted towards the high potential opposite to electron, opposite to electric field. So it will drift along this direction. This is my drift. Okay? So it's drifting along this direction. Now let us say in time t. Let us say in time t, initially the electron was here, and let us say finally it has reached here. So from here it has drifted till this point. Okay, so this distance, if I am calling as L, I can write this as drift velocity multiplied by time. Distance equals to speed multiplied by time. And say that this area of cross section is A. So how many electrons? There is not only one electron, there are many electrons. So if I consider there are many electrons who have drifted from here to here in time t, so how many electrons are there in that volume? Or how many electrons are drifting in time t between those 2 points? So that will help us to get the value of current over here. So the value of current over here will be equal to N multiplied by E divided by T. So what is N? N is the total number of electrons in this volume who were drifting in time T. So how will you find that number of electrons in that? So total number of electrons I can write as N. What is N? Electron density, number of electrons in unit volume, multiplied by this volume. What is this volume? This volume is area of cross section multiplied by length. Area of cross section into length is volume. So volume multiplied by unit density is total number of electrons. Okay, just the same concept of unitary method, and then multiplied by this E, and then divided by time t. Now L I can now write as NA, L I can now write as VD, this is suffix D over here, NaVdT multiplied by E divided by T. T gets cancelled out, so I have got my first relationship, that is equal to NaVdE. This is the relationship between current and drift velocity, NaVdE. And in ISC they ask as simple question like this, write this formula and identify the terms. So here you have to identify the terms, and many a times people make mistake in N. They write number of electrons. No, if you write number of electrons, no marks will be awarded to you. N is not number of electrons. Small n is electron density. Write either electron density or write number of electrons per unit volume to get the full marks over here. And then you have to define A. Just don't write A. A is not area. A here, A does not mean just area. A here means area of cross section. Vd is the drift velocity and E is the electronic charge. Okay, so this is how you define. So this is my area of cross section. This is called area of cross section. Okay. So we have got our first thing. Then we will define one more thing, and that is called current density. Current density is denoted as J, and it's a vector form. It's a vector quantity, okay, whose SI unit is ampere per meter square. That means current density is basically defined as current per unit cross sectional area, where A is area of cross section. Now let's try to find this one. So J equals to I. What is I? I is NA VDE divided by A. A gets cancelled out. So J is equal to N VDE. In vector form, we write a minus sign here when we are writing in vector form. The reason why I am writing in vector form, because drift velocity is because of the electron which is drifting in the direction opposite to electric field, and electric field decides the direction of current. So if the current density is in this direction, that means drifting is happening in this direction. So the minus sign signifies that the electron drifts in the direction opposite to current density or opposite to current. Okay, that's the reason of minus sign. So when this is written when you are writing in the vector form, this is also equally important. So 2 down. Then we are going for Ohm's law. We are also going to see the Ohm's law in under this model. Remember the model, the name of the model is free electron model of electric conduction. Okay. So under this model, let's first quickly let's have a quick recap of Ohm's law. If you remember Ohm's law, it says, if you remember the whole statement which you have learned in class 10, it says that if the physical condition remains unchanged, that means don't change the temperature, area, length, nothing. So when the physical condition remains unchanged, then the current flowing through a conductor is directly proportional to the potential difference applied across it. Okay, so which simply means I is proportional to potential difference. To remove the proportionality sign, we introduce the term 1 by R, and here we know that V is equal to I times of R. Everybody know what is R? R is resistance, whose SI unit is ohm, or denoted as this symbol of omega. Okay. So we will keep this formula alive. So your V by I is equal to R. Okay. Just let us keep this equation alive, because we are going to use this very soon. Let us call this as equation 1. Okay. Now, when you take a conductor and when you apply a potential difference over a length of L, okay, that is a potential difference over here which you are applying here. So because of that potential difference, it develops an electric field E, and this EVL can be written as, remember, if you are for a uniform field we write this as V by D. Remember D, distance, but here distance is how much? Distance is the length of the conductor. So instead of D, I will write L. Okay, so keep that in mind. Now consider one electron over here. This electron is having an initial velocity of u. Okay, and with this, under the experience of electric field, it starts drifting along this direction, or starts gaining speed along that direction. So before it hits the next electron, before the next collision happens, it would have acquired a velocity of v, which can be written as u plus a tau. What is a? That is the acceleration. Who is creating this acceleration? This formula which I am using here is v equal to u plus at, for your comprehension. V equal to u plus at. So u is the initial velocity, and then I am creating an electric field. Because of electric field starts getting dragged along this direction, because of which it gains velocity. So before the next collision, it will gain a velocity of v equal to u plus a tau. Tau is the relaxation time, a is the acceleration, u is the initial velocity. So what we are defining here? We are defining tau. Tau we have used for torque also. Here also we use. So what is tau? Tau is called relaxation time. I repeat, what is tau? Relaxation time. Relaxation time is the time between two successive collisions. That is called relaxation time. But there are not only one electron, there are many electrons. So if I consider that this is V1, U1, tau 1, similarly I can define V2 equals to U2 plus A times of tau 2. So tau here is relaxation time. So tau 1 is the relaxation time for the first electron, tau 2 is the relaxation time for the second electron, and so on. And there are, let us say, n number of electrons. So if there are n number of electrons, this is small v. So if there are n number of electrons, so Vn I can write as Un initial velocity plus A times of tau n. Okay? Correct? Now, again, quick recap, those who are having confusion. So U1, U2, Un, all these are initial velocities of n number of electrons. When you create an electric field, it starts getting dragged along this direction because of the force given by the electric field. So the velocity which it will acquire after time tau is the relaxation time, will be given by this. Also, the average velocity, that is the average drift. Remember, we have to deal with the entire model. We cannot deal with individual electrons. So if I have to deal with the average drift velocity can be given as velocity of 1 plus velocity of 2 plus velocity of 3 plus dot 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 velocity of n divided by n. And this can be now written as V1 you can write as U1 plus A times of tau 1. V2 you can write as U2 plus A times of tau 2, and so on you can continue, plus U3 plus A times of tau 3 plus dot 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 UN, U capital N plus A times of tau n divided by total number of electrons. This is the average velocity. This is equal to, you take U1 plus U2 plus U3 plus dot 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 UN divided by n separately, plus take A common, tau 1 plus tau 2 plus tau 3 plus dot 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 tau n divided by n as my drift velocity. Now remember, this was the initial velocity before applying the electric field, and this average must be equal to 0 as discussed earlier. And this I can now write as A, and then this I can write as tau average. What is tau average? Tau 1 plus tau 2 plus tau 3 plus dot 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 tau n divided by n as my tau average. Now we have to write the value of acceleration. So to find acceleration, we know that force is equal to charge multiplied by electric field. Who is the charge? My electron is the charge. How much is the electric field? Electric field is V by L. So electric field is V by L. This force I can write as mass times of acceleration is equal to EV by L. F is equal to ma, where m is the mass of the electron. This implies acceleration will be equal to EV. I have used this, so I am going to rub this out. So EV divided by m into L. This A I am going to use over here. So my drift velocity expression will be now equal to E V by m into L into tau average. Okay. Henceforth, I will not write tau average. I will just write this as tau only, because book says only tau, I say tau average. So just from henceforth I will just write tau average as tau. So tau automatically means average relaxation time. If I use this in the formula of I, what is I? Remember I was NA V D E. This was the I we derived earlier. If I use this expression in this formula, what will I get? Electron density into area of cross section Vd. Vd is E capital V, the potential, the tau divided by m into L, and then this E, and then this E over here. What is V by I? Just arrange this term. There is a V here. Can you see a I over here? So I'll take this V on this side. So I by V is equal to N A E square tau by ml. This implies V by I will be equal to ml divided by N A E square tau. Try to recall the equation 1. Remember from the definition of Ohm's law. If you remember the definition of Ohm's law, we wrote V equals to IR. And then I said I by V, V by I. V by I is equal to R. And this I wrote as equation 1. That means V by I, this is mlna E square by tau, this should be equal to R. So comparing this equation, on comparing with V by I equals to R, we get R equals to ml by na E square tau. This, my dear students, is an expression of resistance, but let me tell you, this is also one of the form of Ohm's law in terms of average relaxation time. This is one form of Ohm's law in terms of average relaxation time. Okay, and this is also the expression of resistance. Now you can see here on what parameters resistance depends on the given body. Resistance parameter depends on the mass of the electron, the length of the conductor, A is the area of cross section, N is the electron density. Higher the electron density, lesser will be the resistance. Metal has high electron density. That's the reason why its resistance is very, very less. A is the area of cross section, E is the electronic charge has to be, and tau is the relaxation time. So from here, what we need to know is this, and then I will emphasize on this. Don't forget this, the resistance is inversely proportional to relaxation time. Specific resistance. We have to define one more term. Now we call that as specific resistance. Specific resistance is defined as rho, okay, which is defined as the electric field in the conductor divided by current density, E by J. This is how we define specific resistance. In this formula, what is E? E is V by L divided by J. J is current per unit area. As per the definition of current density is current per unit cross sectional area. So I will write as I by A. And electric field, I wrote earlier also, electric field is V by L, where V is the applied potential and L is the length. This is my electric field and this is my potential. So we are using E equals to V by L using the formula V by D or dV by dr, that formula. So V by L, I by A. If I rearrange this term, I will get density as V by L I into A. So I will take V by I separately and A by L separately. Again I got V by A. And what is V by I? Sorry, again I got V by I. And what is V by I? V by I is R. So this I am defining as R A L. This implies R is equal to rho L by A. This is what we learned in class 10. R is equal to rho L by A. Okay? So this is also one of the formula and the important one, where rho is defined as specific resistance. Now let's try to define specific resistance. So I will use this term. Specific resistance is equal to resistance of the body provided if the area of cross section is unit and the length is unit. So if you take a conductor of unit area and unit length, then whatever resistance offered by that conductor is called specific resistance. So specific resistance, what we are specifying? We are specifying this, that the area should be 1 meter square, area of cross section, and length must be 1 meter. In that case, whatever resistance we get, that is called specific resistance, which has a unit of ohm. One of the meter gets cancelled out. So ohm meter is the SI unit of so we get R, and R is a unit of ohm and then 1 meter. So rho is equal to R, but unit is ohm meter. Okay, this ohm meter is the SI unit of specific resistance. Don't forget this. Now let's try to find specific resistance in terms of drift velocity or average relaxation time. So coming back here again, coming back to this, what is rho? Rho is equal to RA by L. This implies R is equal to rho L by A. And what is R? R is also equal to M L divided by N A E square tau. So what will I get? I will get L A gets cancelled out. So specific resistance is equal to M by N E square tau. So here also you will get a relation that specific resistance is proportional to 1 by tau. Okay. Now let's again discuss about tau very quickly. Tau is the average relaxation time. It is time taken between two collisions. Now think about this in this manner. What if you raise the temperature of a substance? If you raise the temperature of a substance, the randomness increases. That means the velocity of the electrons will be more. It will be more thermally agitated. So it will start with it will move in random direction with more velocity. If they move with more velocity, they will collide more frequently. And if they collide more frequently, time between the collision becomes less. That means when temperature is increased, your average relaxation times also, when the temperature is increased, the average relaxation time decreases. When the average relaxation time decreases, your resistivity or specific resistance increases. Okay. Similarly, when average relaxation time decreases, when increasing the temperature, your resistance increases. Okay. And hence, the one which you learned in class 10, that upon increasing the temperature, resistance increases. This is the reason why. So when you increase the temperature, your average relaxation time decreases. When this decreases, your R increases. And I use the word resistivity. Specific resistance is also known as resistivity. Okay, some books write as resistivity also. Okay, and now some important graphs are there which you should know. So if this is my temperature and if this is my resistivity, temperatures are measured in Kelvin. So if it is a conductor like copper, so metal, I will write here metal. For metal, the graph looks like this. As the temperature increases, resistivity increases. For alloy like nichrome, there are some alloys which we use to make resistance. Nichrome. So this is resistivity and this is your temperature. It increases, but increases not that sharply. So here it increases but not that sharp. The rise is slower than metal. So that's the reason why we use alloys to make resistance. And there is another one which we called as semiconductor. Now semiconductor I am just putting here because it is out of context right now. Semiconductor resistivity is the only semiconductor like silicon. They behave in a totally opposite way. For them the resistivity decreases with rising temperature. Okay, so just know for sure that you are remembering these three graphs properly. And the last one is the most important one with one more discussion over here. This one is the important one which they ask for 1 mark. Here let me define conductance. What is conductance? Conductance is reciprocal of specific resistance. It is reciprocal of specific resistance. Okay. So I can write this one as 1 by rho. And how we define rho? Rho is defined as E by J. Correct? In vector form, I can write this one as E equals to rho times of J. But this vector form is not important. There is one more vector form which is more important than this. So if I consider conductance denoted as sigma, so how we are denoting conductance? Conductance we are defining as sigma. Remember, in electricity sigma is conductance, and in electrostatics sigma is charge per unit area. Don't get puzzled. We are running out of notations. Okay, because we have more physical quantities to notify than the number of notations available here. So in electricity we define sigma as conductance. So sigma I can write as 1 by rho. And rho is equal to E by J. That means sigma will become equal to 1 by E by J, and that is equal to J by E. J by E. And now in this case the vector form is J vector is equal to sigma times of E vector. This one is extremely important. This is called vector form of Ohm's law. Vector form of Ohm's law, or also known as microscopic form. Okay, so these are the things which you have to remember. Derivations they have not asked till date. Okay, the very first derivation I is equal to NA VDE, that you should remember. Rest, when you read for once and you understand how things are coming up. The most important is ultimately we have related to temperature, and temperature we can relate the temperature with the relaxation time, and that is the reason why we are deriving everything in terms of relaxation time, average relaxation time, and that is the whole idea of today's class. Okay, then this is how the electrons behave basically in the electricity. What is electron density, what is current density, what is electric field, potential difference, conductance, specific resistance, all these things. So thank you, and we will now from here onwards in the next class we will move towards circuit analysis. Slowly and slowly we will be able to pick up the entire concept of Kirchhoff's law, Wheatstone bridge, and many more things coming up. Okay. So one thing I did not teach here intentionally is the dimensional formula of all these new parameters which are evolving. Like today we saw relaxation time. Since it's time, its dimensional formula has to be time only. M0, L0, T1. Mean free path is distance, so M0, L1, T0. But the things which you have to find is what is the dimensional formula of resistance, dimensional formula for specific resistance or resistivity, dimensional formula for conductance. This thing you should know. Dimensional formula for current density. Okay, so all these things you should do properly. Is there available in any of the book? So just go through it once. Thank you for watching.